Yeah, good morning. Good morning, Steve. It's a pleasure to have the opportunity to talk this morning. Also, I've never directly collaborated with Steve. Steve has, as you will see in my talk, impacted my work and my career in several ways. But what I thought I'd do as the theme of my talk is I want to take Steve's work on laser cooling, which is monumental by itself, and embed it into modern developments in atomic physics. So in that sense, it will show Steve has left work to be done to other people, but it will also show how big really the impact of laser cooling was and how it has revolutionized the field of atomic physics. So let me sort of remind you that atomic physics traditionally is the field where we study atoms and molecules, and that means we observe atoms and molecules. We analyze light emitted by flames or light which is generated here in the neutralized ion beam experiments. These are examples of work I did before I got into laser cooling and Bose-Einstein condensation. And by just analyzing the light, you see many, many peaks. And if you understand all those peaks, you learn something about atomic structure, about molecular structure. You understand how molecules rotate, how molecules vibrate. But this is pretty much the era of atomic physics where we observe nature and understand the structure by means of spectroscopy. A major step forward, as we would say now, is when you use atoms, molecules, and light, not just to understand and observe nature, but really to take control. We want to use light to control atoms and molecules, manipulate matter, and, as you will see in a few minutes, even create new forms of matter which haven't existed. And generically, the way how we can optically control matter is through optical pumping. By using optical excitation, we can make atoms and molecules to go to quantum states which have not been populated before. And different quantum state means the atoms and molecules have new properties. But what is important is we may actually have many initial quantum states, and all the atoms which have been in all these many, many states, if you use sufficiently broadband light, wind up in a single state. So that reduces entropy, that takes atoms from many states into a single state. That is still sort of an interesting area of science. There was just an interesting science paper which I randomly picked, which shows that by optical pumping molecules, you can do some vibrational cooling. But what I really wanted to introduce here is the concept of laser cooling. Laser cooling, which Steve pioneered, can really be regarded as optical pumping of the motional states. So you have particles which move in many, many different translational states with many different velocities, and if you do it right, and that's what Steve did, then you can take atoms from many motional states and put them into fewer motional states, and that reduces entropy and reduces temperature. So this is sort of many years after, sort of a cartoon type way how we completely simplify what laser cooling is about. It's just optical refrigeration. You pump atoms into lower lying states, and therefore their extra kinetic energy is radiated away as light. And of course, we have to make sure that we do things right, because I mean, what makes a difference between cooling atoms and heating atoms? Well, it's the magic of lasers, it's the magic of detuning and Doppler shifts. So if we make atoms, if we irradiate atoms with ready-tuned light, then they absorb light at lower frequency than they emit. And this is, as Carl Wyman has already mentioned, this famous realization of optical molasses. I joined the field in 1990, so I will say a little bit more about that. But in the 10 years before I joined the field, laser cooling was really terribly exciting. In those years, almost every year, a new major breakthrough happened, from beam slowing to molasses to trapping to even lower temperature. And this is sort of a compendium of what are now the standard techniques which every practitioner of laser cooling has to learn. And what are highlighted in red are where Steve did pioneering contributions or the first realization of that. And of course, this was so impactful that it got rewarded. Now, let's come back to 1990. I showed already slides on my earlier work on molecular spectroscopy, and I was intrigued by contributing to maybe what Steve is doing right now, contributing to energy savings and more energy efficiency by analyzing and understanding combustion. So he went from fundamental research to applied research. In 1990, I did the opposite. I did applied research. I was happy and motivated by that, but I wanted sort of the bigger challenges, and ultimately went from the study of hot flames to the study of very, very cold atoms. But just to make the connection, when I was at Crossroads in 1990, I said, I want to really work in a fundamental area of science, and at age 32, well, you shouldn't start completely from scratch. You should use some of the knowledge and experience you've gained. And my experience was in spectroscopy. And it was to a large deal to Steve's pioneering work that it became just obvious. The most exciting area for spectroscopists to be is laser cooling. So I decided to join the field of laser cooling. I wrote letters to the best people in the world, and I got 2 job offers, one from Steve and one from MIT. And it's a little longer story that in the very last moment I decided to go to MIT and not work with Steve. But Steve continued to have an influence and impact my career. So I entered the field of laser cooling, so I entered Steve's world and got immersed into it. This is a picture of my first conference on laser cooling. It was a fabulous conference in 1991 in Paris. See Lake Como in the background, you see all sort of those people. And if I zoom in on here, you see me and you see Steve. So that's where I got to know Steve, where I got really inspired by his summer school lectures. And yes, by hiking one of the mountains together with Steve, I also realized he's also competitive as an athlete. Around those times, there were lots of discussions about this elusive goal, this ultimate goal of laser cooling, namely Bose-Einstein condensation. Sort of not just to optically pump the atoms, to simplify laser cooling, into a few lower lying motional states. The goal was a single quantum state, to do single mode atoms, to do with atoms what has been so wonderfully accomplished with a laser decades earlier. So to, in a way, make atoms really as a single wave and in a single state. So that really required lower temperature and higher densities. And naively, you would think if you want to get all the atoms into the lowest state, you have to cool down very, very much. But what happens is, if you have n atoms, because of bosonic stimulation, the requirement on temperature is reduced. If you have 1 particle per quantum state, due to bosonic stimulation, they all go into the Bose-Einstein condensate. It was actually fun for the preparation of the talk to dig out some slides, which I drew up 10 or 15 years ago, and sort of just go back to these older times. Of course, if you want to do it with laser cooling, you have limitations. So when I joined the field and it became clear that you have limitations in laser cooling due to the recoil, you have limitations in laser cooling due to absorption and to excited state collisions. I should say it was Steve was pushing somewhat further by Raman cooling, by sub-recoil techniques, but in essence, even until now, there's either a temperature or a density limitation of laser cooling. So that means, even now, 10 years later, another cooling technique called evaporative cooling, which I won't explain here, is needed to go to this goal of Bose-Einstein condensation. So that brings me back now to the year 1994. In 1994, at the end of 1994, this was a few years into this final race towards Bose-Einstein condensation, 3 groups were able to combine laser cooling with evaporative cooling. I should actually say that for many years people thought that this was impossible because laser cooling, because of absorption and collision, works best at low densities, but evaporative cooling needs collisions and therefore works best at high density. And when I joined the field in 1990 and asked some people said, well, those 2 things will never go together. Well, it was just a challenge, and in 1994, 3 groups had met this challenge. So there was the Stanford group, the Boulder group, and the MIT group, and I shared with Steve the passion for the sodium atom and for yellow light. And those three groups had different atoms, different traps, different cloud sizes, and all that. And just sort of as an appreciation for the work which was done in Stanford by Steve Chu and Mark Hasevich, at the end of 1994, this was about half a year before BEC became reality, I looked at those experiments and said, gosh, who has the best chances? And actually, my completely wrong prediction was that I would give Stanford the best chance, then MIT, and then Boulder. The result, as we know, was just the opposite. Because with Raman cooling, these sophisticated sub-recoil cooling techniques, and with optical trapping, I thought the Stanford group really had elements in it which were a competitive advantage. Well, maybe it's fair to say that in some sense, Steve and Mark were really ahead of their time. Right now, 10 years later, almost all important experiments on Bose-Einstein condensation are done in optical traps because of Feshbach resonances, spin-ohr physics, all the interesting things we want to do. And it is also possible to do all optical cooling to BEC. So in a way, I think Steve had the vision to pick the right technique, but it was maybe 10 years ahead of his time. So this sort of brings back the moment of competition we experienced. So that was sort of showing how, well, the groups who were involved, the Rice group also joined in, how we were sort of approaching the goal of Bose-Einstein condensation, and of course the summer of 1995 when Bose condensation became a reality and clouds were just shrinking until they were single mode clouds and Bose-Einstein condensation had been accomplished. Now, so I mentioned already that it was the excitement which Steve created with his pioneering work in the 80s which played a major role for me to pick the field. Then it was Steve's direct stimulation with his lecture and the work. But there's another aspect which directly impacted me. By carefully looking through Steve's publication and the work he done, I really realized he's a ruthless experimenter. If he has goals, he is buying equipment, he's changing equipment. So he's always sort of works with a high intensity, works equipment rich, and is not afraid of building complicated machines. And to some extent, I adopted that style. So to kind of put a lot of equipment into a room is something which became partially the trademark of my group. And I've also realized that Steve's approach of just buying good equipment and piling it up and building experiments in a modular way is a way to eventually push the frontiers and make which have been impossible possible. So let me sort of embed that into the bigger picture of atomic physics. So I've mentioned that atomic physics was traditionally about independent atoms and molecules. So spectroscopy, structure, it was mainly about single atoms, but sometimes we had two atoms when they collided and we studied collisions. So atomic physics was about one and two atoms with maybe some interactions between two atoms. Laser cooling was actually a method where atoms were cooled independently. They interacted with the light, but not among themselves. Well, when laser cooling was combined with evaporative cooling, the temperature decreased and the density increased. Well, when the density increases, you get higher interaction energies. And when the temperature decreases, you may find the situation where interactions between atoms become stronger than thermal energies. And this is really a revolution in atomic physics, or which you can say leads out of traditional atomic physics, because we go at this point through a transition from single particle physics to many body physics. And suddenly what became main stage in atomic physics were interacting many body systems. The Bose-Einstein condensate, which we have studied for more than a decade now, played sort of an intermediate role. It is a many-body system. There are many particles through interactions who are sort of synchronized. They form this big wave, which is described with the macroscopic wave function. But it is essentially one wave function for all the particles. So you can say it's just a collection of many atoms doing the same thing. And so therefore, it is still an effective single particle physics situation. The next step, of course, was to make interactions even more dominant, that we cannot describe the system anymore by macroscopic wave function and do the transition to strongly correlated many-body systems. And that is something which has created additional excitement in the last few years, that we were able to take all the techniques of laser cooling and Bose-Einstein condensation and now study strongly correlated system. And the system which has attracted a lot of attention in the last few years are fermions. That's actually something Steve never did. He did laser cooling and Bose condensation. Eventually pathways separate, which is maybe a good thing. Well, just to the non-atomic physicists in the audience, we can do Bose-Einstein condensation only with bosonic atoms. And this will become clearer in the next slide, if we want to use cold atoms to understand and simulate the behavior of electrons, we really need atoms which are fermionic, which consist of an odd number of protons, neutrons, and electrons. So in order to make the fermions do what the bosons do, namely form a happy Bose-Einstein condensate, we have to form pairs of fermions. And really to understand how fermions pair up, this has been a major frontier in the field. So by now having fermionic atoms and by making those fermionic atoms pair, we can put our hands on a piece of physics which has so far only been studied in condensed matter physics. So there was a big breakthrough a few years ago that looks like Bose-Einstein condensates, and it is a Bose-Einstein condensate, but it's a Bose-Einstein condensate not of bosonic atoms, but of fermions which have paired. And what this signals is that fermions were pairing up only because of many-body physics. We are here in a situation where the fermion pairs would be very different or would be non-existent if we just had two fermions in free space. So that now really shows that we observe correlations which cannot be understood in a single particle picture. We are really deeply into many-body physics. And just to entertain you with how far atomic physics has now penetrated questions of phase transition in many-body physics, I just want to sort of show you here one recent result. You can regard superfluidity of fermions as a superfluid dance of partners. The spin-up and spin-down particles have to pair up, and then hopefully they dance, and dancing is a metaphor for superfluidity. But now you can ask the question, which people couldn't actually address with electrons so well, but we could address it with atoms. What happens if, some of the girls are gone and there are more men on the dance floor? And ultimately what we were able to study is that it's a critical point where the fun stops and the superfluid dance comes to an end. And so I don't want to explain those results, but it shows that atomic physics is very visual and we obtain very direct information. So what you see here is with this shell structure, you can see directly that for a while the dancing couples are in the middle, the single men are outside, but if you have even more men on the dance floor, there won't be any dance anymore. So is that the end of atomic physics? Is that the end of the use of cold atoms? No, it's definitely not. For many, many years, and Steve's contributions were in that area, we wanted to control the motion. With laser cooling, reduce the velocity with Bose condensation, have atoms which move as a single mode and which are superfluid. But of course, the next step is not to have any motion at all. And by using optical lattices, which Steve introduced early to the field, you can sort of localize one atom per latticide and therefore completely eliminate the motion. But that means not that you have reached the lowest temperature state. If you have fermions in an optical lattice, the next challenge is if the motion has been eliminated, you have now spin-spin interaction, magnetic interaction, and you want to see spin ordering. So ultimately, and that's what I think will be one of the major topics in the next 10 years to come, after now really no longer dealing with atomic motion. Motion has been completely frozen out thanks to laser cooling, evaporative cooling, and all that. We now want to go to the next level. And this really takes atomic physics to the next level in terms of getting to even lower temperature, just a few nanokelvin, and we need new tools to manipulate and detection. So with that, I can sort of summarize that atomic physicists started to take control of their objects, not just observing them, when they did optical pumping of internal states. Eventually, with laser cooling, evaporative cooling, and Bose-Einstein condensation, we were really taking quantum control, not of the internal states, but of the external motion. Eventually, external motion even became strongly correlated in the form of pairing and lower dimensional physics, but the scientific goal was still to control and understand the motion of particles and bring them to a standstill. But here's the next challenge, which actually goes back now to internal states, internal ordering, spin Hamiltonian and quantum magnetism. But these are now internal states of a many-body system, where these were internal states of single atoms and molecules. So I think with that sort of turn first reductionist to control single atoms at the single quantum level, we are now really building up complexity, and we try to, and this is my last slide, to position atomic physics as an intermediary in understanding complicated materials, some of which may have real-world application. In many-body physics and condensed matter physics, usually the goal is to understand all the complex materials in nature or engineer materials and devices with new properties. On the theory side, people really have simple models with simple Hamiltonians, and it's a big, big thing when you have a new material and the theorist has a theory, whether they're really talking about the same system, because there are so many simplifications. And the role, thanks to laser cooling and all the tricks of atomic physics, which cold atoms can play, is that we can really realize in the laboratory those Hamiltonians and test the simple models, and therefore speed up the overall development in material science. This is now often called quantum simulators. Cold atoms are used to simulate something, but maybe I'm old-fashioned. I would say we're not simulating old systems, we are really realizing new systems. Laser-cooled atoms, Bose-Einstein condensation, and maybe antiferromagnetic ordering in optical lattices are new materials which have been created by us physicists. So with that, I want to conclude. Happy birthday, Steve. Thanks a lot. And you had a big impact on the field, and your legacy is going on.